Hello, Namaskaram. Today we are discussing the topic subgroups. The definition is subset of a group which is itself a group under the same operation. That is, let G star be a group, and you consider a subset S of G. And if this subset S is a group under the same operation star, then this will be a subgroup of G star. So the definition is subset of a group which is itself a group under the same operation. And we have a lot of examples. Consider the group, the set of all complex numbers under addition, and consider the set of all real numbers under addition also. We know that these two are groups. Moreover, R is a subset of C. So this one is a subgroup of C under addition. Once again, consider the set of all rational numbers under addition. And we know that rational numbers is a subset of R and also C. So this set of all rational numbers is a subgroup of R under addition and C under addition. And the last one, consider the set of all integers under addition. We know that as sets, Z is a subset of Q, R and C, and Z under addition is a group. So this one is a subgroup of Q under addition, R under addition and C under addition. Okay, now once again changing the operation, consider the set of all non-zero complex numbers under multiplication, which is a group, and the set of all non-zero real numbers under multiplication is a group. The set of all non-zero rational numbers under multiplication is a group, and we know that as sets Q star and R star are subsets of C star and they are groups. So these two are subgroups of C star under multiplication. Moreover, Q star under multiplication is a subgroup of R star under multiplication also. Here also this Z under addition is a subgroup of Q under addition. Z under addition is a subgroup of R under addition. So we may draw a tower of subgroups here. This is a tower of subgroups. Tower of subgroups means all these are subgroups of this one. All these are subgroups of this one. Here also we have a tower of subgroups. This is a tower of subgroups. This one is a subgroup of these two. This one is a subgroup of this one. Now consider this example. R under addition and Q plus under multiplication. We know that this is a group. This is again a group. And Q plus is a subset of R also. But they are not subgroups. Why? Because the operation is different here. So even though Q plus is a subset of R and both these are groups, Q plus under multiplication is not a subgroup of R under addition because the operation is different here. Now once again you consider this group G star. Let G star be a group, and you consider a subset of G which is G itself. G is a subset of G itself, and we know that G under the binary operation star is a group. So this one is a subgroup of this one itself, and that subgroup is known as the improper subgroup. So this is the largest possible subgroup of G. Now the next question will be, which will be the smallest possible subgroup? For that you consider the smallest possible subset. The smallest possible subset of G, which will be a group, will be the set containing the identity element E only. And we know that this is a group. And this group is known as this subgroup is known as the trivial subgroup. So for any group there exists at least two subgroups. One is the trivial subgroup and the other is the improper subgroup. Now in the last section we found that there exist two group structures of order 4. One is the Klein-Sfor group and the other one is isomorphic to Z4. Now we may consider first we may consider which are the subgroups of Z4. Since Z4 has 4 elements, it has 2 raised to 4, that is equal to 16 subsets will be there. So you can find 16 subsets for Z4. There will be 1 element subsets, 2 element, 3 element and 4 element subsets will be there. And among those 16 subsets, certainly singleton set 0 will be a subgroup, and that subgroup is known as the trivial subgroup. Again Z4, the only subgroup containing 4 elements, which will be a subgroup and which is known as the improper subgroups. So 2 subgroups will be there. Now among these 16 subsets, certainly singleton set 0 and set 4 will certainly be subgroups. And in the remaining 14 subsets, only you may verify that only Z02 will be a subgroup. So Z4 has only 3 subgroups: the trivial subgroup, the improper subgroup, and the non-trivial proper subgroup as 02. So we may draw the subgroup diagram for Z4. We have Z4 here, and the next is Z02 is the another subgroup. This is the subgroup diagram of Z4. That means this 02 and 0 are subgroups of Z4. Once again, Z0 is a subgroup of 02 and Z4. Okay. Now we may look at the Klein-Sfor group B. Here also 4 elements, so 2 raised to 4, 16 subsets will be there. Among those 16 subsets, the subgroups are, I shall draw the subgroup diagram. The subgroups are singleton set E will be certainly a subgroup, which is the trivial subgroup, and the others are the 2 element subset EA will be a subgroup. Another singleton 2 element subset EB will be a subgroup, and EC also will be a subgroup. And we have the improper subgroup B also. So this is the subgroup diagram for the Klein-Sfor group B. Now another example is, you consider the group Rn under addition. Rn means the set of all n tuples of real numbers, and you consider the subset S. You consider the subset S of Rn. That means you consider the set of all n tuples with the first entry as 0. I belongs to R. You consider this subset S and verify whether this S under addition is a subgroup of Rn under addition. Certainly this S is a subset of Rn. Now you have to verify whether this under S under addition is satisfies our group properties. So first we may look for the closeness. You choose 2 n tuples with the first entry as 0. So 0, A2, A3, etc. An plus 0, B2, etc. Bn. This is equal to 0, you will get another n tuple. You will get another n tuple with the first entry as 0. So this one certainly belongs to S. That means S is closed under addition, the operation addition. Now for associativity will certainly hold. What about the identity element? The set of all tuple with all the entries as 0 will act as the identity element. And what about the inverse? The tuple 0, minus a2, minus a3, etc., minus an will be the inverse of 0, a2, a3, etc., up to an. So our S satisfies all the properties of a group, and hence it is a subgroup of Rn under addition. Okay. So in order to check whether a subset S of a group G be a subgroup or not, we have to verify whether S satisfies all the group axioms. But here we have a little more compact, easy criteria, and the result says that a subset H of a group G is a subgroup of G if and only if A B inverse belongs to H for all A B belongs to H. This is an if and only if results. So it has two parts. The first part says that a subset H of a group G is a subgroup. The assumption is H is a subgroup. Then the result is A B inverse belongs to H for all A B belongs to H. Conversely, if A B inverse belongs to H for all A B belongs to H, then H will be a subgroup of G. We may try to prove this result. In the first part, the assumption is H is a subgroup of G, and by using that assumption, you have to prove that A B inverse belongs to H for all A B belongs to H. Now, A B belongs to H, and our assumption is H is a subgroup. Then A B belongs to H implies that A B inverse also belongs to H, because H is a subgroup and B is an element of H, and hence its inverse also should be so A B inverse also belongs to H. Now again, since H is a subgroup, H is closed under the operation, and A and B inverse are two elements of H. This implies that A B inverse also should belongs to H. So that part is very simple. Our assumption was H is a subgroup of G, and by using that assumption we have shown that A B inverse belongs to H for all A B belongs to H. Now the reverse part is, in the reverse part our assumption is for all A B belongs to H, A B inverse belongs to H is our assumption, and by using this assumption we have to prove that H is a subgroup of G. That means we have to show that our H satisfies all the group axioms. First, what about associativity? Since G is a group and H is the elements of H are elements of G, associativity will automatically hold. There is nothing to prove. Now, using this condition, I am choosing two elements A and A from H. A B belongs to H implies that A B inverse belongs to H. Now the elements we have chosen are A and A from H. Then by using this condition, this implies that A inverse belongs to H. Now A inverse is the identity element E. That means E belongs to H. So the identity element E is an element of H. Now once again I am choosing two elements from H, and they are, the first element is E. By this condition E is an element of H, and the second element is A belongs to H. So we have chosen two elements from H. Once again you apply this condition. A B belongs to H implies that A B inverse belongs to H. Now E A belongs to H implies that E A inverse belongs to H. Now E A inverse is A inverse, so A inverse belongs to H. So you have three conditions. The three group axioms are satisfied by H. Associativity, there exists the identity element and there exists an inverse for each element of H. And the last step is we have to prove that H is closed under the this binary operation. For that you choose, once again you choose two elements A and B from H. Now A and B belongs to H, and this condition implies that every element of H has got an inverse in H also. So since B belongs to H, B inverse also belongs to H. Now this condition implies that AB belongs to H implies AB inverse belongs to H. So AB inverse belongs to H implies that by using this condition AB inverse belongs to H. That is AB belongs to H. That means our H is closed under the binary operation. So all the four conditions for a group are satisfied by H, so H is a subgroup of G. Now we may apply that result in some examples. Consider the group GL of NR under multiplication. In the last section we found GL of NR. The elements of GL of NR are n by n real matrices whose determinant is non-zero, and under multiplication GL of NR is a group, we know. Now you consider two subsets of GL of NR. The first subset G1 includes all n by n matrices with the determinant 2. Now you have to verify whether this subset is a subgroup of this one. We may use that result, that is H is a subgroup of G. H is a subgroup of G if and only if A B inverse belongs to H for all A B belongs to H. This is the result. So you choose two elements from G1. Elements of G1 are n by n matrices with the determinant 2. So you choose two elements A and B from G1. A and B are elements of G1 means this implies that determinant of A is equal to determinant of B is equal to 2. Now we have to verify whether A B inverse belongs to G1 or not. Now we have the result that we have two results. The first one says that determinant of A inverse is equal to 1 by determinant of A. And the other result is determinant of AB is equal to determinant of A into determinant of B. So by using these two results, you consider AB inverse. Consider AB inverse. For AB inverse 2 belongs to G1, its determinant to be 2. Now consider the determinant of AB inverse. By using this result, determinant of AB is equal to determinant of A into determinant of B. This one can be written as determinant of A into determinant of B inverse. And this is equal to determinant of A into, now determinant of A inverse is equal to 1 by determinant of A. So determinant of B inverse is 1 by determinant of B. Determinant of A is 2 and determinant of B is also 2. So 2 into 1 by 2, that is equal to 1. So determinant of A B inverse is equal to 1, not equal to 2, so that A B inverse does not belongs to G1. A B inverse does not belongs to G1, so that G1 is not a subgroup of GL of NR. Now consider this subset. Here G2, the subset G2 consists of all n by n matrices with the determinant 1. So in order to verify this result, you choose two elements from G2. Let A B belongs to G2. A B belongs to G2 implies that determinant of A and determinant of B are 1. Now for A B inverse to belongs to G2, its determinant should be 1. Once again you apply these two results. Now determinant of A B inverse is equal to determinant of A into determinant of B inverse by using this result. And this is equal to determinant of A into, now determinant of B inverse is 1 by determinant of B. But determinant of A is equal to 1 and determinant of B is also 1. This is equal to 1. So determinant of A B inverse is equal to 1. That means our A B inverse belongs to that group, that subset G2. So by our criteria, G2 is a subgroup of GL of NR. So this result gives a simple method to verify whether a subset of a group is a subgroup or not. Okay. Now another important category of subgroups are cyclic subgroups. Before defining cyclic subgroup, let us have a new notation. Let G star be a group. G star is a group and you choose one element A from G. By A raised to N, we mean A is operated N times. And here the operation is star. So A raised to N means A star, etc. N times. And the second notation is by A raised to minus N, we mean A inverse is operated N times. That means A raised to minus N is equal to A inverse star A inverse, etc. star A inverse. So these are the two notations we require. Okay. Now we have the definition of cyclic subgroup. Before the definition, consider the group Z10. Consider the group Z10. And you know the operation in Z10 is addition modulo 10. You consider this group and choose the element. And choose the element 4 belongs to Z10. Now you take the powers of 4. Now 4 raised to 1 is equal to 4 itself. But now 4 square means A raised to N means A is operated N times. So 4 square means 4 is operated 2 times. And the operation here is addition modulo 10. So this is equal to 8. Now you find 4 cube. 4 cube means 4 is operated 3 times. So 4 is operated 3 times and the operation is addition modulo 10. So 4 plus 4 plus 4 becomes 12 and 12 under addition modulo 10 is 2. Now what is 4 raised to 4? 4 raised to 4 means 4 is operated with 4 times and the operation is addition modulo 10. So this is 16 and 16 under addition modulo 10 becomes 6. Now you continue this work. Now what is 4 raised to 5? 4 raised to 5 is equal to 4 operated with 4 5 times. And the operation here is addition modulo 10. So 5 4s becomes 20 and 20 addition modulo 10 is 0. Now what will be 4 raised to 6? While finding 4 raised to 6, we have to operate 4 6 times. And the 5 4 becomes 0. So the remaining term will be 4. What will be 4 raised to 7? These values are repeated. 4, 8, 2, 6, 0, those values will repeat. So by finding the powers of 4, you will get the values. You will get the values 0, 4, 8, 2 and 6, or we may write in the order 0, 2, 4, 6 and 8. This is the set we are getting by taking powers of 4, and you may verify that this will be a subgroup of Z10, and that subgroup is known as the cyclic subgroup generated by 4, because all these elements we are getting by taking powers of 4. So this subgroup is known as the cyclic subgroup generated by 4, denoted by this one, cyclic 4. So by a cyclic subgroup we mean let G star be a group, and A belongs to G. By the cyclic subgroup generated by A, this is the notation, we mean we are continuously taking the powers of A where n belongs to Z. This is the definition. This is the definition of a cyclic subgroup generated by an element. We have one more example. You consider the fourth roots of unity U4, and you know the elements of U4 are 1, I, minus 1 and minus I. We know that U4 under multiplication is a group, and you choose the element minus 1. We have to find the cyclic subgroup generated by minus 1. So you continuously take the powers of minus 1. First, minus 1 the whole raised to 1, that is equal to minus 1. The second one is minus 1 square, that is equal to 1. What about minus 1 cube? Minus 1 cube is equal to minus 1. So now you will repeatedly get these two values, minus 1, 1, minus 1, 1, or you may stop whenever you get the identity element. In U4, the identity element is 1. So while taking the powers, you may stop whenever you get the identity element. So the cyclic subgroup generated by minus 1 is equal to 1 and minus 1. Here also you may verify that property. While taking the powers of 4, whenever we get the identity element 0, there you may stop, because the next powers will give you repeatedly we will give you these values. So this is the definition of the cyclic subgroup generated by an element, that is equal to set of all A raised to n where n belongs to Z. Okay, that's all for from this section subgroups. Thanks for watching.